average American driver spends roughly $1,890 a year on gasoline based on DOE data in a 25-mile-per-gallon fleet average. Drivers in Japan spend roughly half that amount on identical commute patterns. The Japanese fleet average sits at 47 miles per gallon, while the American fleet average sits at 25. Same vehicle class, same commute distance. Here is the part the auto industry rarely explains in any marketing material. Toyota sells the same Camry in both countries with the same engineering specifications. The difference is not the car. The difference is what most American drivers were never taught about operating it efficiently. This breakdown covers the 6-layer Japanese protocol for cutting fuel consumption by up to 50% in real-world driving conditions. 3 of the 6 layers cost nothing to implement and require only behavior change. The other 3 are mechanical interventions that total under $20 in materials. The data comes from the U.S. Department of Energy, the Japan Automobile Federation, and Oak Ridge National Laboratory, not from forums, not from internet anecdotes. One specific layer determines whether a driver hits 30% savings or the full 50%. Most American service shops never check this component during routine maintenance. It costs $10 in materials and 10 minutes of time to address. We get there shortly. For now, one question. Why does the same Toyota cost twice as much to operate in America? Quick disclaimer before we start, the tips and guides in this video are for educational purposes only. Every vehicle is different, so please use this information at your own risk. We are not responsible for any damage or injury that may occur. When in doubt, always consult a professional mechanic. The Japan Automobile Federation, known as JAF, is not a marketing organization or a private interest group. It is the Japanese counterpart to AAA, founded in 1963 with roughly 19 million members as of recent reporting. Their eco-driving research dates back 3 decades and forms the backbone of national driver education programs. JAF's national driver training campaigns measured something direct and reproducible. Behavior change alone, with no vehicle modifications and no special equipment, delivered an average 10% reduction in fuel consumption across program participants. That figure is documented in the International Energy Agency's overview of Japan's heavy-duty vehicle fuel efficiency policy. It is not a marketing claim, it is published institutional research. The Japanese government layered a second system on top of driver training. The Top Runner program, run by Japan's Ministry of Economy, Trade, and Industry, drove fleet-wide fuel economy improvements of 24.1% between 2009 and 2020. This combined manufacturer engineering targets with national driver behavior protocols into one coordinated framework. The United States has no federal equivalent of either system. There is no eco-driving requirement in any state's driver license curriculum. There is no national behavior measurement program tied to fuel data. The gap between American and Japanese fuel efficiency is not just engineering, it is education. For the average American household, that 10% behavior gap alone equals $189 a year. Compounding from there, with sensor maintenance and oil grade selection, gets serious quickly. The data shows 3 mechanisms quietly burning fuel before most drivers notice anything wrong with their vehicle. Mechanism 1. Aggressive driving. This is not just speeding. The U.S. Department of Energy, working with Oak Ridge National Laboratory, quantified the cost in detail. Aggressive acceleration and hard braking lower fuel economy by 15 to 30% at highway speeds. In stop-and-go traffic, the penalty climbs to 40%. The Oak Ridge study, led by researcher John Thomas in 2017, tested identical vehicles under 3 driving styles and confirmed energy-conscious driving consistently outperformed normal driving by measurable margins. For the average American driver, aggressive habits cost between $283 and $567 a year in wasted fuel alone. Speed compounds this mechanism further. Above 50 miles per hour, fuel economy drops sharply due to aerodynamic drag scaling. The DOE's published calculation puts every 5 miles per hour over 50 at the equivalent of paying an additional 27 cents per gallon. A driver cruising at 75 miles per hour instead of 60 is paying nearly $1.35 extra for every gallon they burn at highway speeds. Mechanism 2. Physical resistance. This covers tires and aerodynamics. Oak Ridge ran a controlled test on a 2009 Toyota Corolla in 2014. Tires at 75% of recommended pressure cost 2 to 3% mpg across all measured speeds. Tires at 50% pressure cost 10% at 40 miles per hour. The DOE estimates that 3.56 million gallons of gasoline are wasted in the United States each day from underinflated tires alone. 24.1% between aerodynamic drag scales with the square velocity, which means it grows fast above 50 miles per hour. More than half of an engine's energy output at highway speed goes to fighting wind resistance. A roof-mounted cargo box can lower city fuel economy by 8% and highway economy by up to 25%, according to DOE published figures. Mechanism 3. Sensor degradation. This is where the gap opens widest, and where most American drivers have no idea their vehicle is bleeding fuel. A modern engine relies on two sensors to control fuel injection: the mass airflow sensor and the oxygen sensor. Both degrade gradually over normal driving miles. Both can be cleaned, recalibrated, or replaced. Most American shops do not check either during routine service. These three mechanisms account for roughly 30% of the gap between an inefficient driver and an efficient one. The remaining 20%, the part that pushes the system to 50%, comes from a single component. Most mechanics never inspect at all. The American driver was given conventional advice that has not been updated since the 1970s carburetor era. Four conventional practices in particular continue to drain wallets at the pump every single week. First, driver education without efficiency training. No U.S. state requires eco-driving instruction for licensure. Drivers learn how to operate a vehicle. They never learn how to operate it efficiently. Second, routine service without sensor diagnostics. A standard oil change at most American shops includes a multi-point inspection on paper. That inspection rarely covers MAF sensor cleaning or oxygen sensor response time verification. These checks take time and they do not generate parts revenue. The shop has no economic reason to perform them. Third, the premium gas myth. The DOE confirms that higher octane gasoline does not improve fuel economy unless the engine was specifically designed to require it. Most cars on American roads run on regular without any performance penalty. Drivers who upgrade to premium without manufacturer requirement spend an estimated $200 to $400 a year for no measurable benefit. Fourth, outdated warm-up advice. The 5-minute idle warm-up is a habit carried over from carbureted engines. Modern fuel-injected engines, including every Toyota, Honda, and Nissan sold in the past 3 decades, are designed for immediate, gentle driving from cold start. The correct protocol per published OEM owners' manuals is 30 seconds of idle, then drive gently until the temperature gauge moves. 5-minute idles burn fuel and add carbon deposits to the cylinders. Each of these 4 practices moves money from the driver's wallet into someone else's revenue line. And there is one component the American service industry has every reason to leave alone. Cleaning it takes 10 minutes. The materials cost less than a sandwich. Most shops cannot bill enough to make it worth their time. That component is where the Japanese method starts. That component is the mass airflow sensor, also called the MAF. It sits between the air filter and the engine intake. Its only job is to measure how much air flows into the cylinders. The engine's computer uses that single reading to calculate exactly how much fuel to inject for every combustion cycle. When the MAF gets contaminated with oil, mist, and fine dust over thousands of miles, it underreports airflow by a small but consistent margin. The computer compensates by dumping extra fuel into the engine to keep the air-fuel ratio safe. Mechanics at Firestone Complete Auto Care and CRC Industries Technical Documentation report fuel economy losses of 2 to 8% from mild contamination and 10 to 30% from heavy contamination. The fix is a $10 dedicated MAF cleaner spray and 10 minutes of work in the driveway. That is one of 6 layers in the Japanese protocol. Here is the full system. Layer 1. Smooth acceleration. Terry Penny, a technology manager at the DOE's National Renewable Energy Laboratory, described the technique with one sentence: drive as if there is an egg between your foot and the gas pedal. That single mental model accounts for up to 30% of the savings, according to DOE track driving studies. It costs nothing to implement. Layer 2. Maintain 55 to 65 miles per hour on the highway. Above 50 miles per hour, every 5 miles per hour adds 27 cents per gallon in penalty per DOE calculations. A driver dropping highway speed from 75 to 60 saves roughly $1.35 per gallon burned at cruising speed. Layer 3. Tire pressure at the upper end of OEM door jamb specification, not the maximum number printed on the sidewall. The pressure listed on the sticker inside the driver's door. Properly inflated tires recover up to 3% mpg according to DOE data and last meaningfully longer. Layer 4. MAF sensor cleaning. Every 30,000 miles. Dedicated MAF cleaner only. Carb cleaner, brake cleaner, or contact cleaner will destroy the hot wire element and require a $200 replacement. Layer 5. Manufacturer recommended oil grade. The DOE confirms a 1 to 2% mpg improvement from using the correct grade. Japanese OEMs specify 0W20 for most modern Toyota and Honda engines built in the past 15 years. Layer 6. Zero unnecessary idling. Idling burns 0.25 to 0.5 gallons per hour per the Argonne National Laboratory 2015 study. Restarting the engine costs roughly 10 seconds of fuel. Now, the honest part, the 50% in the title is the stacked maximum. It is what is achievable when every layer is implemented. The driver currently has multiple bad habits, and the vehicle has degraded sensors at the same time. The average driver who applies all 6 layers will see 25 to 35% improvement. A driver who already drives smoothly and maintains the vehicle will see 5 to 10%. The ceiling is real and documented. It is not the average. Layers 1, 2, and 3 are behavior. They are free. Layers 4, 5, and 6 are mechanical. One of them is the difference between a 30% improvement and a 50% improvement. We get to that next. Layer 4 inches detail, the mass airflow sensor. The MAF uses a heated element, usually a thin platinum wire or a hot film, to detect how much air passes through the intake. Cooler intake air carries away more heat from the wire. The sensor measures the cooling rate and translates it into an airflow value the computer can read in real time. 2 contaminants degrade this reading over normal driving miles. Oil mist from the positive crankcase ventilation system, also called the PCV system, and fine dust that bypasses the air filter through normal porosity. Over 30,000 to 60,000 miles both build up on the heated element. The sensor underreports airflow. The computer compensates by injecting more fuel than the engine actually needs. Mechanic reports collected from Firestone Complete Auto Care, CRC Industries technical documentation, and ASE-certified independent shops describe consistent losses ranging from 2 to 8% for mild contamination to 10 to 30% for severe contamination. The cleaning protocol uses dedicated MAF sensor cleaner spray, available at any auto parts store for $8 to $15. Total job time, including drying, is 15 to 20 minutes. One critical limitation: only dedicated MAF cleaner can be used. Brake cleaner, carb cleaner, contact cleaner, or any general solvent will dissolve the resin coating on the wire and destroy the sensor permanently. A replacement runs $200 to $400 plus labor. The wire must also air dry completely with no wiping and no compressed air before reinstallation. Layer 5 inches detail, motor oil grade. The DOE confirms a 1 to 2% mpg improvement from using the manufacturer-specified oil grade rather than a heavier viscosity. The mechanism is internal friction reduction. Thinner oil flows more easily between moving parts at startup and at full operating temperature. Modern Japanese engines from Toyota and Honda are engineered for 0W20 specifically. The cylinder bore tolerances, bearing clearances, and oil passage geometry assume that exact viscosity. Heavier oils such as 5W30 or 10W30 do not protect the engine better in these designs. They cost mpg and add wear during cold starts. The action item is straightforward. Check the oil cap or owner's manual and match the grade exactly without upgrading to thicker oil. Layer 6 inches detail, idling elimination. The Argonne National Laboratory 2015 study quantified idling cost at 0.25 to 0.5 gallons per hour. A driver who idles 5 minutes per day during cold weather warm-ups burns roughly 0.04 gallons daily, equal to about 15 gallons per year wasted. At $3.5 per gallon, that habit costs $52 a year for a behavior that produces no engine benefit. Modern fuel-injected engines reach operating efficiency through driving load, not idle time. Toyota, Honda, and Nissan owners' manuals all specify the same protocol. 30 seconds of idle, then drive gently until the temperature gauge moves. Sierra Club analysis of fuel-injected drivetrain design confirms the carbureted-era warm-up advice no longer applies to any vehicle built in the past 3 decades. The math projection. The DOE's Eco-Driving Feedback Device Study found average drivers improve fuel economy by about 3% with awareness alone. Drivers actively applying the techniques improved by about 10%. The Edmunds 2008 tire pressure study, tracking 60 employees over 8 weeks, recorded 2 to 3% MPG gains from monitored inflation alone in real-world conditions. Stack everything. A vehicle with a 27 MPG baseline, an average commute pattern, and a driver who currently has several inefficient habits projects mathematically to 34 to 38 MPG after full protocol implementation. That is a 26 to 41% improvement range, depending on the vehicle's sensor condition and the driver's starting habits. The real-world average lands inside that range. Not at the 50% ceiling, but not at the 5% floor either. All 6 layers stacked, mathematically, deliver up to 47% in real-world testing scenarios. There is one driving habit that determines whether a driver reaches that ceiling or stalls at 30%. That habit is what we cover next. Before the habit that pushes this system from 30% to 50%, hit subscribe if the math has already saved you money. This video, next week, breaks down the Japanese throttle body cleaning protocol that recovers another 8% on top of everything covered today. The stacking effect compounds video to video. Each layer adds margin to the wallet. That habit is anticipation distance. The technique appears in every JAF commercial driver curriculum and every Japanese eco-driving training module. The mechanic explanation is direct. Most American drivers look 3 to 5 seconds ahead of their vehicle on the road. Japanese training expects drivers to look 12 to 15 seconds ahead for traffic flow changes, signal patterns, and brake patterns from vehicles ahead in the lane. The result is fewer hard brake events, fewer hard accelerations, and smoother momentum across the entire commute. Those inputs compound with Layer 1 to push smooth driving from 20% savings closer to 30%. Here is what the data confirms directly with documentation. Every layer covered above carries DOE, EPA, or Oak Ridge National Laboratory verification. The mechanisms are reproducible. The percentages have published peer-reviewed support. Here is what Japanese instructors recommend based on 3 decades of curriculum design. Anticipation distance is the layer that separates the 30% driver from the 50% driver. It has not been independently quantified by Western laboratories with a single dedicated study, but every Japanese commercial driver program treats it as a core technique. JAF training materials estimate 5 to 8% additional savings from anticipation alone. Now, the 1-0-year compound math. Average driver baseline at the current DOE national fuel cost average, $1,890 a year. A 30% improvement, typical for full protocol implementation by an average driver, drops the annual cost to roughly $1,454. That saves $436 every year. A 50% improvement, the stacked maximum for a driver with multiple bad habits and a degraded vehicle, drops the annual cost to roughly $1,260. That saves $630 every year. Over 10 years of vehicle ownership, the savings compound to between $4,360 and $6,300 in real dollars at current fuel prices. Reframe that number for a moment. $6,300 is enough to pay for the entire fuel cost of the first 3 years on the next vehicle. Stated differently, it pays back the original purchase price of a used Camry in fuel savings alone over a single decade of driving the car you already own. There is one habit Japanese mechanics universally avoid that costs American drivers another $200 a year. It has nothing to do with the engine. Here is the full protocol consolidated as a checklist anyone can implement starting tomorrow. Layer 1, smooth acceleration. Cost, 0. Time, every drive. Mental model, imagine an egg between your foot and the gas pedal. Layer 2, maintain 55 to 65 miles per hour on the highway. Cost, 0. Time, every highway trip. Penalty for ignoring, 27 cents per gallon for every 5 miles per hour above 50. Layer 3, tire pressure at the upper end of OEM door jam specification. Cost, a $5 pressure gauge if you do not already own one. Time, 5 minutes monthly and before any long trip. Hard limit, never exceed the maximum PSI printed on the tire sidewall. Layer 4, MAF sensor cleaning. Cost, $10, dedicated MAF cleaner spray. Time, 15 to 20 minutes, including full air dry. Frequency, every 30,000 miles. Hard limit, dedicated MAF cleaner only. No general solvents under any circumstances. Layer 5, manufacturer recommended oil grade. Cost, same price as any standard oil change. Time, every regular oil interval. Action, match the grade printed on the oil cap exactly, with no upgrading to thicker oil. Layer 6, 0 unnecessary idling. Cost, 0. Time, every parking event longer than 30 seconds. Protocol, the 30-second drive-off warm-up replaces the 5-minute idle warm-up. And the hidden 7th item that pays back the open question from earlier in the breakdown: vehicle weight and aerodynamic load. Drivers carrying 100 extra pounds in the trunk lose 1% mpg per published DOE figures. Drivers using roof-mounted cargo boxes lose up to 25% on the highway at cruising speeds. Both habits are free to fix tonight before tomorrow's commute. Empty the trunk of items that do not need to be there. Remove the roof rack between trips that actually require it. Total system cost, less than $20 in materials. Total setup time, 30 minutes one time, plus a different way of pressing the gas pedal from this drive forward. The 6-layer protocol is not Japan's secret. It is what every American driver could implement with information that was never delivered to them by their licensing curriculum, their service shop, or their owner's manual. Japan codified this knowledge into a national curriculum 30 years ago. The United States did not. That is the entire structural gap behind the 50% MPG difference between identical Toyotas in Tokyo and Toledo. Kaizen, the Japanese philosophy of continuous improvement, applied across factory floors and household routines, applies directly to vehicle operation. Small discipline practices compound. The driver who tracks tire pressure monthly, maintains 60 miles per hour instead of 75, and cleans the MAF every 30,000 miles is not following a trick. They are running a system. Japan does not have fuel-saving technology Americans do not have. Japan has fuel-saving discipline Americans were never taught. The next time you fill up, the question is not whether the method works. The question is whether you will drive differently for the next 30 days to find out. Run the system for 30 days. Track baseline MPG before starting. Most cars display lifetime average right on the trip computer screen. Then track the after. Drop both numbers below in the comments, along with the layer you started with first. Layer 1, the driving behavior layer, is where most drivers see the fastest jump in measurable MPG. If the math saved you a future $6,000 in fuel costs over the life of your current vehicle, the like button signals YouTube to send this to other drivers wasting money at the pump every week. Subscribe for the throttle body breakdown next Wednesday. That layer recovers another 8% on top of everything covered today. Every script, edit, and voiceover on this channel is crafted with real human expertise, not mass-produced content. If this helped you, subscribe for more.